Hi, everyone. I took this picture last year at the MIT Museum. It's a mind-blowing machine designed by the one and only Claude Shannon. And this machine uses electric and mechanical relays to solve for the final moves of chess. And I also find the naming very fitting, because at that time, the world's top scientists think that solving chess is the end game to AI itself. And then in the next 70 years, Shannon got way more than his wildest dreams. And in fact, we beat chess 40 years ago. We solved Go, Dota, and poker 10 years ago. And this year, we won a gold medal in IMO and also a Nobel Prize for protein folding. And these are things that make our parents proud. Right? Our AI is on track to master anything that can be reduced to a sequence of strings. And in many ways, we have conquered the world of bits. And now enter the world of atoms. So please meet Rainbow. And she's an ape living in the Dubai Zoo. And you can see this is a real video. Like she drives a golf court attentively, patiently, no road rage. I don't know about you, but I think she drives better than maybe half the humans I know. And then look at her extended family, playing tennis, musical instruments, fishing, right? Piecing together the puzzles, flipping through the books. It's so fascinating to watch. And these activities are so simple and trivial, yet even what an ape can do seems somehow far beyond our strongest AI and baddest robots. So really, what's left in AI is not anywhere as glorious as winning a few more gold medals, but it's a journey to the mundane, things that you take for granted in a messy, unpredictable, and chaotic world, and things your parents are unimpressed about. Right? For example, you leave on a Monday morning after a Sunday hackathon, and then you come back home to a clean house and a candlelit dinner. And you could not tell if a human or robot had been there. And that, my friends, is the physical Turing test. It is so mundane, so boring, so deceptively simple. But I argue it's the next, or perhaps the last, grand challenge for AI. So now the question is, how do we solve it? Really, it boils down to just two things at the end of the day for any AI system: the data strategy and the model strategy. And let's start with data. All right. So a certain great man said that LLMs are running out of data, that the internet is the fossil fuel of AI. And I would say the LLM scientists, they are so spoiled. Look at us, look at roboticists, what do? Right? This is a typical episode that we collect on a humanoid robot at NVIDIA's headquarter cafe. And this is what the data looks like if you plotted the motor control actions. Right? These data, can you find it in the fossil fuel? You can't scrape this data from Wikipedia, unfortunately. So we have to collect our own. It's called human fuel that we have. So there's a brute force way called teleoperation. You have the person wear a VR device, and then you stream the finger and the wrist pose to a robot. So you, in real time, retarget to humanoid with dexterous hands. And on the right-hand side is an egocentric view of what the robot sees. And there's a fundamental physical limit to it. It's going to be up to 24 hours per robot per day. And actually, who am I kidding? It's probably close to 4 hours per robot per day, because the robot god is not always merciful. The robot throws tantrums, right? 4 hours per day, we call it a good Tuesday. So what do, right? The humanoid robots are actually pretty brittle. Well, there are much simpler, much more robust robots out there, right? So this is a snippet from the famous Stanford Aloha project. You have these bimanual grippers, it's static, and you can do these long horizon tasks, and you can do it continuously. The robot breaks quite rarely, and even if it breaks, you can quickly replace it. And you also have these wheeled-based robots with grippers that you can teleoperate also very easily, right? Using things like the Joy-Con. And you can do whole body teleoperation, and the robot doesn't fall down because it's a wheelbase. So if you plot these robots on this 2D plot, where the x-axis is the embodiment, or the hardware complexity of data collection, and the y-axis is how scalable is this embodiment, then you can put something like a static bimanual manipulator here, maybe around 10K hours over a couple months if you're really good at operations. And for the wheel robots, maybe a little bit less. They're harder to tally up. And the humanoids with dexterous hands, they're the hardest, they're the most brittle, and maybe 100 to 1,000 hours over a month. So here, if we draw this line, these are the data collection methods that require the robot in the loop. And the best we can do is something like 10 to the fourth power. So can we do better? Can we have data collection methods that don't need robots in the loop? And then we can go to this physical limit by striking out the robot, and your robot will be very thankful. They're happy robots because you no longer need them, right, during the data collection. So there are ways like this, where you just put an egocentric camera on a human and have the human go out and collect the data, right? It's a lot more scalable. And humans throw a lot less tantrum than robots. And we put it on a table, right? For the human videos, the cost is very, very low. But the visual gap, the sensor gap, the action gap from the robot you deploy to is huge. Because humans, right, we have way more degree of freedom, and our hands are just built very differently. And then for teleop, extremely costly. You need to train people to adapt to those hardware, but you don't have visual, sensor, or action gap. So can we do something in the middle? That's a sweet spot. Actually, you can. Here's an interesting idea. How about we design a mechanical exoskeleton that's one-to-one mirroring the robot hands joints and physical constraints? And in fact, this method, you can apply that to different dexterous hands. This is in spearhead and the X hand, and you can design the mechanical components to exactly mirror them. So here, on the left-hand side, is if you do a task directly yourself. So that is the human video approach. So it's really fast, right? Very easy. And on the right-hand side, you set up the teleoperation device where you have the dexterous hand in the loop. And you can see it's a lot more awkward because the hand, right, doesn't always follow you. It's very hard. So somewhere in the middle, you can just use this exoskeleton to collect the data directly. And this is a method called DexUmi that our team will present at Coral very soon in Korea. And this type of technique is what we call data wearables, where the cost is quite low. You just need to 3D print some components. And there's a little bit of visual gap, right? Because the camera still sees your hand. It's not directly the robot hand. But there's no sensor gap and no action gap. And if we plot them on this data collection plot, for the human videos, you can probably easily scale to maybe 1 million hours, right? Very quickly. And the data wearables are not that far away, right? They're closer to a robot, and they're a little bit slower, but you can scale massively because you don't have the robot in the loop. And now, here's the question. Which one do you pick? What do you do, right? You have all of these options. Do you go all in teleop? Do you go all in human videos? What do you do? Well, remember, we cannot be as picky as Ilya. Ilya can be picky. We roboticists, we can't afford to be. We need all the data that we can get. So really, the strategy here is to take the entire integral under this curve that I'm calling the embodiment integral. And that is the inner ring on this data strategy. You integrate over all the embodiments you can get. And so far, we still only talk about the top of a data pyramid. So it's the real data, no matter it's a human or robot. You can have it 24 hours per robot per day, or you can remove the robot. It's physically grounded, but still it's very costly. You're still limited by the physical limit, and that's the human fuel. And we still need all the web data, right, to be mixed into the training, and that's the fossil fuel, right? It's an unstructured string of bytes, and you can generate exabytes per day. Now, what I'm most excited about is where it's in the middle, and that is the synthetic data. And it could be the nuclear fuel to power the next generation of robots. And for synthetic data, it's infinite in principle, but it's limited by Ph.D. brain cycles because you actually need to come up with very innovative ways to make use of synthetic and generate synthetic data. It's also limited by our GPUs, all right? So here's a message approved by my boss. The more you buy, the more you save. It's gotta be synthetic data. I'm unbiased. This is the way to go. So Jensen asked me, how do you build a nuclear reactor for robotics? This is Eureka, a technique that allows us to train high degree of freedom hands to do pen spinning at human level. And I admit, I'm a subpar human. I can never do pen spinning. I gave it up long before in my childhood. So it's very glad to see my AI avenging my poor skills. So how do you get the data to train this very complex pen spinning? And the answer is there is actually no supervised data set involved. It's all done by reinforcement learning in massively parallel simulations running on the GPU, because luckily, all the physical equations are just matrix multiplications. And CUDA is the best for matrix multiplication. And actually running on CUDA, you can simulate reality at 10,000 times faster than real time. And that's how you generate all these data by itself. Now the question is, simulation is all great, but how do you transfer to the real world? It's a very simple technique that we use all the time. You just vary the gravity, the friction, and the weight across all of your 10,000, 100,000 environments in parallel. It's called domain randomization. And why does it work? It works because suppose an AI model is able to master 1 million realities with different physical parameters, then it's highly likely to zero-shot the 1 million and the first reality, which happens to be our physical world. And that's the first principle of the simulation hypothesis. So we build digital twins of things like robot dogs in Isaac simulation, and then you can zero-shot it in the real world. And it doesn't matter which robot. As long as you can simulate, you can zero-shot. And this is a 4-finger hand doing cube spinning. And this was a really impressive one that we got in 2023, where we instantiated the robot dog on a yoga ball in simulation. And the yoga ball is bouncy and it's soft, and we didn't even simulate any of that. You just do aggressive domain randomization, and then you can run a zero-shot. You can have a robot dog walking on a yoga ball on the streets. I think it's straight out of a Black Mirror episode. And my friends told me that this may be super dog performance compared to their dog. They tried it on their dog. And if we apply this technique and instantiate an army of humanoids, then we can train something of a neural network to control the humanoid body, to stay balanced, walk, run, and do agile motions. And this small neural network that we trained is only around 3 million parameters. No, it's million, not billion. It's only 3 million parameters, and it captures the subconsciousness of the motor coordination that we humans do all the time at millisecond scale. And we transfer that to the real world. So normally, the video demos you see online are all sped up, right, like 5x speed. But here, I actually slow down the videos so you can appreciate the motions a bit better. This is a work called ASAP from our team, and we're able to transfer these agile skills onto the humanoid. So when you visit NVIDIA office, this is a building called Voyager, you might run into these little guys, and don't be a stranger, say hi to them. So we have these robots sometimes running in the office, and then this is one single model doing the jump, doing the running with huge amount of human likeness, because we actually pre-train this on human motion capture data. And then it does the signature Tesla dance. And some of the robots work too hard. So occasionally we take them to our robot hospital. Yeah. But no robots harmed during filming. So if we put the synthetic data generation methods on this 2D plot, on the x-axis is the diversity of the data it generates. On the y-axis is the scalability measured by speed. Then for digital twins, you can build one-to-one replica of the world and objects in it, and you can simulate it at up to 1 million frames per second. And these are classical, still based on classical physics engines, but how to accelerate it. and we call this simulation 1.0. So can we do better? Can we do better than curating every robot, every environment through artists by hand in the simulations? And of course we can. We can use 3D generative models to generate all kinds of object assets. We can use diffusion models to vary the texture of a kitchen. And you can also use LLMs to author the XML files, and then you combine them into this exponential number of procedurally generated rooms. And putting all of them together, this is a project, an open source project called RoboCasa, where we procedurally generate diverse tasks composed of different objects, locations, robots, and appearances. And how do you collect data? How do you generate data in the simulation? So let's say you teleoperate inside the simulation, not on a real robot, inside the simulation, and you collect one human demonstration, like this, and you replay it using different renderings and the procedural generation of the environment, right? Then you get a variety of data already. And instead of repeating, picking up an apple from left to right, why don't you generate picking up the apple from right to left, from top to bottom? All these actions can be mechanically generated. So you have a procedural generation of the action as well that we call GR00T mimic. So you start with one human demo, and then with environment generation, you multiply into n, and with motion generation into n times n, and I promise you this is the only math we're going to do today. And you're mixing this data with the real, and you can still tell that column 2 and 4 are from kind of a game engine style texture, but it looks roughly similar. And you blend it in, and you can do sim plus real data co-training, and we have shown that it greatly improves your performance. So put it on this plot. It's not really digital twin that we're doing, right? It's not identical, but it's kind of a distribution that's similar. So we call it simulation 1.5, the digital cousin of the world. So it's still based on a physical engine, but now it's generative. It's a hybrid between different generative methods and a physics engine. And now, try to simulate this. This is just a random picture I got from Google Image, right? Just look at all the textures, all the complexity, right? There are like transparent glasses, there's fluid simulation, right? There's bread, deformable objects, and napkins. How do you simulate that? I have no idea. Maybe this thing will take an artist a very long time to do. So if we look at graphics, right, the evolution of graphics, on the left-hand side is a game from 1993. And it takes the graphics community 30 years to get somewhere on the right-hand side. Yet it only takes the machine learning community 2 years to go from the left to the right. I mean, it's still hilarious, but at least it's physically accurate on the right. Right? And this is the Sora, the VO models of the world. These are video generative models that's completely learned and data-driven. There is no physics engine in the loop. It's all just a text in and a blob of pixels out. And that's it. That's all the rendering and the physics engine compressed into a neural network. So if you recall at the beginning, right, I showed this video from our cafe. And actually, I tricked you. There's not a real pixel in this video. It is all dreamed up by a video world model technique that we call GR00T dreams. So how it works is we fine-tune a video world model that has been pre-trained on hundreds of millions of hours of YouTube videos, and then we fine-tune it on the teleoperation data that we collect in-house, which is tiny. But because of the pre-training, the video model now understands how the robot moves, how the mechanical structure works. So now you have a customized video generator just for your robot. And then you can prompt it in any way you want. So on the left and right-hand side, you actually start with the exact same initial frames. And the only difference is the prompt. And let me start the simulation on the left. So you can see pick up the apple and place on the pan. And then on the right, from the same initial frame, but with a different language, it's able to simulate and generate a video of the counterfactual world. And because it's a video model, it doesn't care how many objects are there. It all runs the same. So you can have these complex scenes, and you give it a different prompt, and it's even able to select the right hand because actually the spray bottle is closer to the left hand. So on the right-hand side, I decided that I need to use the left hand to pick up the spray bottle. And we also run it in NVIDIA Cafe. And all of these are generated by video, by the Good Dreams video model. And you can see it's able to do all these complex reflections super, super well. Just imagine doing all of these using ray tracing and artist-curated objects, right? It's going to be incredibly hard. And my favorite example is on the second column, top row. So that's a robot playing ukulele. And the video model has seen a lot of humans playing ukulele. And we never collected any teleoperation data on ukulele. It doesn't even happen in our training set. But it kind of maps the robot to a motion that looks like playing the instrument. And by mixing all this data, right, real data and dream data, co-training, you achieve things like action generalization. So these are actual robot execution videos where you give it new verbs that has never seen in teleoperation before, and it's able to generalize. And you can also run it in novel environments, like we train the robot in the lab, and then we zero-shot it in NVIDIA Cafe. So just like LLMs, that are superposition of millions of personalities, I like to think of video world models as a superposition of millions of visual realities. And prompting it in different ways will lead to all kinds of possible futures. And if you put it on this figure, it is the neural physics engine. It is soft, learnable end-to-end. It is programmed by data instead of graphics engineers. And for lack of a better phrasing, I'm calling it the digital nomad, as it's wandering through the multiverse of a diffusion model. So decision time, which one do you pick? 1.0, 1.5, or 2.0? And again, let me remind all of you, can't be picky. Ilya can do his thing, but we cannot. So we need all of it. And we take the integral over this curve. And that is the second ring, the synthetic integral. So really, the data strategy is actually a double integral strategy. You integrate over all the data, all the embodiments, and the synthetic data is actually mostly orthogonal to embodiments, so you can have video world models on all kinds of hardware. And you see where I'm going, all right? This is the philosophy that I'm following, and it can be summarized in only 4 words. It's a data maximalist principle and a model minimalist, right? We can build very complex pipelines of the data, and I welcome any addition of new pipelines for data. But I would not tolerate any increase in model complexity. The model has to be a clean artifact that compresses all the tokens generated by the data maximalist strategy into let's say, a 2 billion artifact. So recall, this is what the robot sees, right? As the input is a video, and this is the output. It's a set of high-dimensional continuous floating vectors. So the role of a vision language action model, or VOA model, is to take the pixels and the language instructions and then output the floating numbers. And we want this model to be as end-to-end as possible. So we roughly divide it into 2 modules. It's still 1 model, but we roughly divide it into 2 modules, inspired by the thinking fast and slow. So the big circle here is a system 2 module. We call it the reasoning engine, right? It's conscious, it's deliberate, it's effortful, and it generates discrete values, like text tokens, to the chain of thought and planning. And then you need a system 1 module that is unconscious, reactive, and fast, and it generates continuous vectors for fast motor actions. So it's really something like a rendering engine, right? And actually, a process like diffusion model is exceptionally good at this, because it's good at modeling these high-dimensional floating vectors. So you can think of it as you have a rough noise of an action, and then through the system 1, you denoise and clean it into something that you execute on the robot. And putting it all together, this is the GR00T N1 and N1 1.5 models. You tokenize the images, you tokenize the language, you go through a VOM backbone, and you push it through a diffusion transformer, and finally you get a float vector out. And that's it. That is a model. Very clean, minimalist. So group model, we apply it to a diverse scenario. Sometimes it could be romantic, but sometimes when it's upset, it will spill the champagne everywhere. And we also apply it to factory settings. So actually, these two robots are both running the group model. So it's the same model, but it's able to take different prompts and then act differently given these scenarios. And if you connect different embodiment heads to the diffusion transformer, you can easily achieve cross-embodiment. So you can have a single model that can solve for grippers, single arm with dexterous hands, and full humanoids. You just put a few more modules on the output layer. So data maximalist and model minimalist. And we open source all our models and all of our training recipes in various papers and GitHub repos. So this is the Isaac Groot repo. And we are also on a quest to democratize physical AI. So in the foreseeable future, all the Groot models, all the new versions will be open source. So go ahead and git clone. Now, what's next? What's next after all of this? I would say that right now we're building the physical AI, but very soon in the next couple of years, the physical AI will become physical APIs. So most of human civilization, you have the world of atoms, that is the messy, chaotic physical world, and then the human labors is applied to the world of atoms to reduce the entropy and make useful things out of it. And the physical API will replace this layer, so we can connect the world of atoms to just software. And there are so many possibilities. If we have the physical AI API, we can have all the things, all the goodies that we have been building for LLMs, like physical prompting. How about MCPs, but embodied MCPs? And agentic workflow, but now here is the agentic fleet, where an agent can run on the physical API to coordinate not just one, but a hive mind of robots. And then building on top of these primitives, these infra layers, you will have programmable factories. What you need, however low volume, you just program it, and then there's something end-to-end delivering it. And you can also have, what I'm very excited about, is self-driving wet labs. A lot of the science, the biology, and the chemical experiments now have humans in the loop, right? And you can have self-driving labs, just have robots doing scientific experiments all day long, and we'll have drug discoveries accelerated at the speed of forward propagation. And then on the very top, with all of this, there will be a new emerging physical skill economy that people share their specialized skills or cuisines that they build, and then you can download from a physical app store. And now, this is a question I get asked a lot of time, so let me just put it here as an FAQ. When are we get there? So here's my answer. I think we tend to overestimate the short term and underestimate the long-term impact. So I don't know when it will first happen, but I can estimate the latest time that will almost certainly happen. And we put this on a time scale here, right? So this is year 2025. And in 2012, that is the beginning of deep learning, of AlexNet, right? Everyone hails AlexNet as the crown jewel of AI. But do you guys have any idea how crappy it is? It's doing object classification at 62% success rate, which means in 1/3 of the time, it's not able to recognize a dog from an airplane, for example. So probably all these chihuahuas look like blueberry muffins to AlexNet. And that's 2012. And 13 years later, we, as the AI community, we won a gold medal for IMO, and we won a Nobel Prize. And it's only been 13 years. And the pace of technology is never linear. It is exponential. And we extrapolate another 13 years. We are in the middle point between AlexNet and 2038. And let's just throw in 2 more years, round it up because Ph.D.s procrastinate. So in 2040, is it too much to ask that our most mundane becomes possible? That we'll probably have a much better robot than Rambo. And I think the probability of that is close to 100%. So it's a day in 2040. You come home from work, and instead of folding laundry or scrubbing dishes, you sit down to a candlelit dinner. You spend a quality evening with a partner, your kids, and your parents. And the robots will just fade away into background ambience. And everything is so mundane that you wouldn't even notice. And it's only 2040. In a blink of an eye, we'll get there. And we were born too late to explore the Earth, and a bit too early to travel the galaxies. But I think we were born just in time to solve the physical Turing test. Thanks, everyone.